Next topic is a multi-relational characterization of dynamic social network communities. So this slide discusses the multi-relational characterization of dynamic social network communities. So the overview of this slide is it explores how communities in online social media are characterized using computational approaches. These approaches are informed by the insights from the social science. So what is the motivation? So motivation is a human community as meaning making ecosystem. So we will see point by point. The first one is schematics evolution. So the human activity generates emergent semantic artifacts that evolve over time. The second is social nature. Since human activity is inherently social, human social networks become critical spaces for meaning construction. The third one is community identification, which is recognizing real human networks involves identifying people's interactions through meaningful activities. The fourth is conceptual associations. Communities contribute to forming stable associations between concepts and artifacts in a structured and coherent manner. This slide highlights the motivating applications for the multi-relational characterization of dynamic social network communities. So the first is by analyzing human networks and evolving concepts, the community discovery can lead to new insights and advancements in information search and decision making. So the example applications include context sensitive information search and recommendation. So it means the discovered communities provide valuable context based on objects, activities and time. This aids in identifying the most relevant information for an information seeker. The second is content organization, tracking, and monitoring. So, the community structure may be used to reflect the social sharing patterns. This information can facilitate better content organization, enable efficient tracking, and monitor user generated social media content. The third is behavioral prediction. So this is for analyzing community dependency can offer insights into behavioral patterns. So the behavioral prediction models can anticipate the dynamics of individual behavior based on social interaction. So this slide presents the data characteristics and challenges of the multi-relational characterization of dynamic social network community. So the key points include large data volumes, which means a social media platforms like blogs, Facebook, Twitter, Tik and Flickr generate massive amount of data daily. So the key characteristics of the online social media data includes one is voluminous. The amount of data and the rate of data production can be enormous. The second is dynamic. So the user's online activities are logged with timestamps offering detailed insights. These continuous records help observe the evolving nature of social interactions and interest. The third is context rich. So the social media platform provide various ways to manage and share media objects. Contextual data includes text, images, videos, and user interaction, offering diverse insights. So in this slide, we will see the approaches for these three problems. So the first approach is mutual awareness. So mutual awareness is a bidirectional relationship. It evaluates how well two individuals, in this case, for example, bloggers are aware of each other. In social network analysis, mutual awareness is fundamental for identifying and characterizing communities. If two users are mutually aware, it strengthens their relationship within the network, supporting the concept of tight knit community. Then the second is measuring mutual awareness. So the measure of the mutual awareness is done using a random walk based distance measure called commute time. The commute time refers to average number of steps a random walk would take to travel from one node to another and then return. The smaller the commute time, the higher the livelihood that the two blockers are aware of each other. So this measure is particularly useful for understanding the latent or indirect connections in the network that may not be immediately visible. Then, by applying this commute time method across a network, the system estimates the probability of mutual awareness between all possible logger pairs. This provides a clearer picture of how connected or aware different users are, helping to extract more accurate and meaningful communities. The last point is the experimental results. So the results are promising based on standard evaluation metrics. So what are the metrics that will can be considered are modularity. So which measures the strength of the division of a network into communities. The second is precision and recall. So which evaluates the accuracy of the community detection algorithm. The third is the normalized mutual information. So which accesses the quality of community extraction. So these metrics can be considered for evaluation in the experiment results. So this slide covers the second problem under multi-relational characterization of dynamic social network communities using FaceNet. So the FaceNet, it is a community detection using historical and current data. So we will see what is FaceNet. So FaceNet is a dynamic community detection algorithm designed to analyze and track how communities evolve over time. Unlike static approaches that only consider a snapshot of a network at one moment, the FaceNet factors in both current network data and historical information. So, this dual approach enables a more accurate and stable understanding of community structures in dynamic social networks. So this FaceNet evaluates the network's community structure at specific step by using observed network data and a prior distribution from historical community structures. So this technique helps in identifying consistent and evolving patterns in the social media platforms where user interactions often shift. So the next is scalability and effectiveness of this FaceNet. So this FaceNet is designed to be scalable, meaning that it can analyze large social networks efficiently. Its capability to integrate past and present data makes it more reliable in recognizing meaningful and persistent communities. Social media networks like Twitter, Facebook, or LinkedIn are ideal scenarios for applying FaceNet, where community trends fluctuate and new patterns emerge. This slide focuses on the third problem in our study. So just using MetaFact for community analysis in dynamic social networks. So what is MetaFact? So MetaFact, it is a tensor factorized framework for community detection. So it is described as a first graph-based tensor factorization framework for analyzing the heterogeneous social networks. So heterogeneous social network involve multiple types of entities and relationships such as users, posts, tags, and comments on the platform like Twitter or Facebook. The metafact effectively models these complex relationships to extract meaningful communities from vast social media datasets. So the key concepts of this metafact is first one is tensors. So tensors are multidimensional arrays that generalize matrices to represent higher order relationship in data. So in the context of the social networks, a tensor can capture user-user interaction, user post engagement, user topic associations. So the tensor factorization breaks down these complex structures into simpler components, revealing the underlying patterns in the network. This slide also mentions the use of the metagraph, the metagraph framework. So the metagraph is a relatively hypergraph where nodes represent different entity types. For example, users, post or tags, and edges represents relationship between these entities. Unlike traditional graphs, the metagraphs can capture multiple relationship types simultaneously, making them ideal for analyzing multi-relational and multi-dimensional data. So in a Twitter network, a metagraph could capture how users retweet, like, and comment on different posts while also identifying trending topics. So the advantages of the metafag are scalable, adaptive, and meaningful insights. So this metafag is scalable for large-scale social media data, making it suitable for platforms with billions of users. The second advantage of this metafag is adaptive. So it effectively tracks changes in the network structures over time, allowing it to identifying dynamic communities. It can also extract actionable insights from the complex data set, which can be applied to marketing, cybersecurity, or behavioral analysis. So here in this slide, the approaches for three problems in the multi-relational characterization of dynamic social network communities is summarized. So first, the mutual awareness. So it refers to the bidirectional relationship that measures how well two users, such as bloggers, are aware of each other. So the example for this is on platforms like Twitter or Instagram, two influencers interacting frequently may demonstrate high mutual awareness, which reflects their close relationship within the social circle. The second is mutual awareness expansion. So it is an extension of the mutual awareness that uses a random walk based distance measure called commute time. So it estimates the probability that two users are aware of each other even if they don't have a direct connection. So a random walk simulates movement within the network, capturing both direct and indirect relationships. So the example for this mutual awareness expansion is consider two bloggers who don't follow each other but frequently engage with the same set of influencers. So commute time analysis could reveal a higher mutual awareness livelihood. The third is FaceNet. So FaceNet is a dynamic community detection framework that models the evolution of communities over time. So the example for that FaceNet, as discussed earlier, in platforms like Facebook or LinkedIn, professional communities may shift as users switch jobs or roles. The FaceNet could seamlessly adapt to these changes. The fourth is MetaFact. So Metafag is a graph-based multi-tensor factorization framework designed for analyzing of your heterogeneous social network. So the heterogeneous social network means it can have multiple entity types such as users, post, tags, and relation types like likes, shares, or comments. So the example for this metafag is on a YouTube, users watch video, leave comments, and share content. So the metafag can analyze these interactions to uncover hidden communities of shared interest. So the first diagram A illustrates how the mutual awareness builds over time. The arrow represents interactions or engagements. For example, comments, like, shares between users, leading to a gradual increase in mutual awareness. The plotted graph at the bottom shows how mutual awareness is tracked as a function of time, highlighting the periods of frequent interaction. So the example for this graph may be if you consider two bloggers frequently commenting on each other post, over time their mutual awareness grows, which can be visualized using this awareness curve. The second diagram, that is a B, is mutual awareness expansion. So this image introduces the concept of mutual awareness expansion using a random walk based distance measure. So the red dashed line represents the connection between two users who may not directly interact but are indirectly connected through mutual acquaintances. Random walks simulate how information travels through a network, capturing hidden relationships. So the example for this B is two bloggers who don't directly follow each other but engage with common influences can still exhibit a high probability of mutual awareness as shown by the expanded path here. The third diagram, that is C, shows how FaceNet tracks the evolution of communities over time. So the nodes represents users and the edge between them change as time progresses. The model ensures stability by minimizing the abrupt changes in the community assignments. The darker connections might represent stronger relationships while lighter ones indicate weakening ties. So the example for this C is a group of users discussing a specific trending topic might slowly shift to a different subject over time. A FaceNet will capture this gradual change while maintaining the core community structure. The last approach, that is D, which is called as metafact. This is a more complex presentation showcasing the use of the metagraph for analyzing multi-relational heterogeneous networks. The nodes represent different entities such as users, documents, projects, and tags, while the colored edges signify various types of relationships. So by applying multi-tensor factorization, MetaFact can uncover patterns across those diverse interactions. So the example for this MetaFact is in a corporate network, a MetaFact can analyze how employees collaborate on projects, publish documents, and share tags to identify productive teams or detect knowledge silos. So the conclusion of this four approaches is, so we have started with the mutual awareness, which is introduced it as a foundation of community formation. Then it is expanded to mutual awareness expansion, so which explains how indirect relationships are identified. Then it moves to discussing your FaceNet, so which emphasizes its strength in tracking the evolution of communities. Then it concludes with MetaFact, which highlights its ability to analyze multi-relational data for deeper insights.